There is something out there that should not exist, not in the way that strange things sometimes defy expectation. A rare species, an unusual mineral, an unlikely coincidence. This is different. What the James Webb Space Telescope has been finding at the edges of the observable universe is not merely unusual. It is structurally impossible, according to everything we thought we understood about how the cosmos came to be. And the more carefully scientists examine the data, the more certain they become. Either the instruments are lying, or the universe is far stranger than our best theories have ever allowed. Let that settle for a moment. For decades, the story of the cosmos felt, if not comfortable, at least coherent. The Big Bang happened approximately 13.8 billion years ago. In the first fractions of a second, everything, all matter, all energy, all of space itself, erupted from a single point of infinite density. Over billions of years, gravity pulled hydrogen and helium into clumps. Those clumps ignited into stars. Stars forged heavier elements and exploded. And from that wreckage came everything else. Planets, oceans, molecules, life, thought. The slow accumulation of knowledge that eventually produced a mirror called science, through which the universe could begin to understand itself. It was a long story. It was a hard story. But it had a certain terrible elegance. And then the James Webb Space Telescope opened its golden eye, and the story started to crack. If this kind of exploration moves something in you, the kind of question that makes the floor feel less solid beneath your feet, then stay. Subscribe to the channel, leave your like, and let's follow this together, all the way to the edge. The telescope was designed as a machine of deep time. Its primary mirror, 18 hexagonal gold-coated beryllium segments arranged into a surface 6.5 meters wide, was built to catch the faintest, oldest light in existence. Light that has been traveling since the universe was less than 1 billion years old. Light so stretched by cosmic expansion that it arrives not as visible wavelengths, but as infrared. Invisible to human eyes, legible only to instruments of extraordinary sensitivity, unfolded into images by algorithms, and translated into something we can finally see. When the first James Webb images were released to the public in July 2022, the reaction was almost visceral. People wept. Scientists who had spent careers working on the telescope found themselves at a loss for words. What appeared on screen was not a chart or a graph or a simulation. It was light, ancient, impossible, beautiful light. Galaxies visible in the background of images taken in mere hours. Galaxies that would have taken weeks to detect with Hubble. The depth of the cosmos laid bare in a single frame, each smear of color representing a system of hundreds of billions of stars, so distant that the light reaching the detector had left its source before Earth existed. But beauty was not the only thing the images contained. Within months of the telescope's first deep observations, astronomers began noticing something that made their confidence falter. Among the ancient galaxies appearing at the farthest distances, at redshifts so high that the objects were being seen as they existed fewer than 1 billion years after the Big Bang, there were galaxies that did not fit the model. Not by a small margin. Not in a way that could be attributed to measurement error or instrument calibration. These galaxies were massive, structurally mature, orderly in some cases, with the distinct shapes and organized architectures that, according to every theory we have, require billions of years of evolutionary time to produce. They were there too early. The universe, according to our models, does not work quickly. Structure formation, the process by which gas clouds collapse into stars, stars organize into galaxies, galaxies merge and evolve into the layered, complex systems we see around the Milky Way, is a slow gravitational grind. The first stars are thought to have ignited around 100 to 200 million years after the Big Bang, in an epoch astronomers call cosmic dawn. The first galaxies, tiny and fragile and irregular, should have assembled gradually after that, building mass over hundreds of millions of years before anything resembling a mature galaxy structure could exist. And yet, the Webb images are showing galaxies at redshift 10, redshift 12, redshift 16, corresponding to moments when the universe was less than 500 million years old, in some cases less than 300 million, that look nothing like fragile early structures. They look like galaxies that have already lived long lives, like galaxies that started forming almost immediately after the Big Bang, as if the universe skipped the slow phase, as if something in the earliest moments of cosmic history was accelerating structure formation at a pace our models cannot account for. One study, published in early 2023, identified a sample of galaxies observed by Webb that appeared so massive for their epoch that they were described in the paper's title, without hyperbole, as impossibly early. The lead author, astronomer Ivo Labe, told reporters that if these objects were confirmed as massive as they appeared, they would contain more mass than the standard model of cosmology permits to exist at that time. They would represent, in total, more stellar mass in a small patch of early sky than all the stars in all the galaxies in the observable universe should have produced by that point. Read that again. More stars than should exist, not by a small excess, by orders of magnitude in some cases. The initial response from the cosmology community was careful, as it should be. Science does not abandon successful models on the basis of early data. There are many ways for observations to mislead: lensing effects that amplify apparent brightness, contamination from nearby light sources, errors in the photometric redshift, estimates that place galaxies at their apparent distances. All of these possibilities were seriously considered. Many still are. But as the data has continued to accumulate, as more observations have confirmed the presence of these structures at extreme redshifts, the discomfort in the field has grown. What began as an anomaly is becoming a pattern. And patterns at this scale are not easily dismissed. What makes this more than a technical problem is what it implies about the nature of knowledge itself. The standard cosmological model, technically known as lambda CDM for its inclusion of a cosmological constant and cold dark matter, is not a guess. It is one of the most tested, most mathematically sophisticated, most observationally confirmed frameworks in the history of science. It correctly predicts the large-scale structure of the universe, the abundance of light elements forged in the minutes after the Big Bang, the precise pattern of temperature fluctuations in the cosmic microwave background radiation, the accelerating expansion of space driven by dark energy. When a model correctly predicts phenomena across 13 billion years of cosmic history, you do not abandon it lightly. You do not abandon it at all, unless what you are seeing cannot be explained any other way. And that is precisely the question the scientific community is now wrestling with in real time. Is this a calibration problem? Is this an issue with how astronomers estimate galaxy masses from infrared light? Is there new physics, some process of early star formation, that was more efficient, more explosive, more rapid than anything in our models? Or is something more fundamental at stake? Some assumption buried deep in our cosmological framework, accepted for so long that it has become invisible, now quietly failing at the edge of the observable universe? You are standing at a peculiar moment in the history of human understanding. A machine built to answer the deepest questions we could articulate has sent back information we did not expect and cannot yet fully interpret. The universe, viewed from its outermost accessible edge, does not look the way it should. And this this is only the beginning of the problem. To understand what the James Webb Space Telescope is actually seeing, you first need to understand what looking at the universe really means, because it does not mean what it seems to mean. When you look up at a clear night sky and see a star, you are not seeing the star as it is. You are seeing the star as it was. Light moves fast, 300,000 kilometers per second, fast enough to circle the Earth 7 times in a single second. But the universe is so incomprehensibly vast that even at that speed, light takes enormous amounts of time to cross it. The nearest star to the Sun, Proxima Centauri, is so far away that the light reaching your eye left its surface over 4 years ago. The Andromeda Galaxy, the large spiral neighbor to the Milky Way, visible as a faint smudge on dark nights, is 2.5 million light-years away. When you look at it, you are seeing it as it existed 5 million years ago, before modern humans existed, before the species that would eventually build telescopes had yet emerged. The universe, in other words, is not a place. It is also a time. Looking outward and looking backward are the same act. This is the principle the James Webb Space Telescope weaponizes. By capturing light at extremely long infrared wavelengths, light that originated as ultraviolet and visible radiation billions of years ago, but has been stretched by the expansion of space until it is barely recognizable. Webb can, in a very real physical sense, see the past, not simulate it, not infer it, actually detect the photons that were emitted when the universe was young, that have been traveling ever since, and that are only now, after billions of years in transit, ending their journey in the detector arrays of a telescope floating 1.5 million kilometers from Earth. This is why the telescope was positioned at a point called L2, the second Lagrange point, a gravitational equilibrium between the Sun and Earth, where an object can remain relatively stationary while orbiting the Sun. From L2, with its massive sun shield blocking heat from the Sun, Earth, and Moon simultaneously, Webb can cool to temperatures near absolute zero. It must. The infrared light it is designed to detect is so faint, so cold, so ancient, that any thermal interference from the telescope itself would drown it completely. The instrument must be colder than the radiation it seeks. Think about what it means to build a machine whose operating temperature must approach the theoretical lower limit of heat in the universe in order to hear the echo of its very beginning. To make this tangible, consider the concept of redshift, the phenomenon that makes distant, ancient light visible to Webb. When an object moves away from you, the light it emits gets stretched. The wavelengths elongate. The light shifts toward the red end of the spectrum. The farther away an object is, the faster space is expanding between you and it, and the more its light is stretched. At sufficiently large distances, this stretching is so extreme that light originally emitted as ultraviolet is redshifted all the way into the infrared. Astronomers use redshift as a cosmic ruler. An object with a redshift value of 1 is being observed as it looked when the universe was about half its current age. A redshift of 6 means you are seeing the object as it existed when the universe was less than 1 billion years old, in its first 7% of existence. When astronomers report that Webb has detected galaxies at redshift 10, 12, or even 16, they are saying that we are seeing light that left its source when the universe was a few 100 million years old, when the cosmos was, cosmically speaking, still a newborn. At that age, the universe should have looked something like this. Imagine the first few 100,000 years after the Big Bang as a dense, glowing fog, a plasma so hot and opaque that light could not travel freely through it. This is the epoch astronomers call recombination, when the universe cooled enough for electrons to bind to protons and form neutral hydrogen for the first time, and the fog lifted. For the first time, light could travel. The faint glow of that moment still fills the universe today as the cosmic microwave background radiation, the oldest light we can detect, a whisper from 380,000 years after the beginning. After recombination came what is poetically called the cosmic dark ages. There was matter, hydrogen and helium and traces of lithium, but there were no stars yet, no sources of light. The universe was expanding, cooling, and deeply, profoundly dark. Gravity was doing its slow work, pulling hydrogen gas into subtle density variations that had been imprinted by quantum fluctuations in the earliest fractions of a second of existence. Those clumps were growing, but they had not yet crossed the threshold into ignition. The first stars lit up somewhere around 100 to 200 million years after the Big Bang, in what astronomers call cosmic dawn. These primordial stars, sometimes referred to as population 3 stars, were unlike anything that exists today. Composed almost entirely of hydrogen and helium, with none of the heavier elements that later generations of stars were seeded with, they were likely enormous, burning hot and fast, living brief, violent lives measured in millions of years rather than billions. When they died, they seeded space with the heavier elements forged in their cores and in their explosive deaths: carbon, oxygen, silicon, iron, the raw materials that later stars and planets, and eventually, life would be built from. After cosmic dawn, galaxies began to form. The Standard Model is explicit about how this should have happened. Slowly, hierarchically, bottom up. Small structures first. Tiny proto-galaxies assembling from the wreckage of the first stars. Then those small galaxies merging and growing over hundreds of millions of years, gradually building the large, complex, organized systems we see in the modern universe. There is a reason the Milky Way is a massive, structured spiral with a central bulge, distinct arms, and a supermassive black hole at its heart. It took billions of years to become that way. It merged with dozens of smaller galaxies. It consumed material from streams of infalling gas. It evolved. That evolution takes time. It requires time. Time is the one ingredient that cannot be substituted. This is why what the James Webb Space Telescope is finding is so disturbing. When astronomers look at the galaxies Webb is detecting at the highest redshifts, in the time window between 300 and 800 million years after the Big Bang, they should be seeing the very first stages of galaxy formation. Tiny, messy, irregular clumps of gas and young stars, barely distinguishable from the surrounding cosmic medium. Instead, in a growing number of cases, they are seeing objects that carry the signatures of age. Galaxies with defined structures, galaxies with what appear to be old stellar populations, stars that formed early and have already evolved, implying that star formation in these systems began earlier still. Galaxies containing more stellar mass than the Standard Model predicts should be possible at that epoch, given how quickly the cosmos was expanding, how dilute the gas clouds were, how slow gravitational collapse was expected to be. The model predicts a certain amount of mass. The observations suggest more, sometimes much more. There is a number that cosmologists use to describe the maximum rate at which gas can theoretically collapse into stars, a physical ceiling imposed by the thermodynamics and gravity of early cosmic conditions. Some of the Webb galaxies appear to be saturating that ceiling, or exceeding it, as if the early universe was forming stars, not at the expected rate, but at the maximum theoretically possible rate, across wide regions of space from the very beginning. No one expected that. Not quite. And as the data accumulates, as the pattern solidifies across hundreds of confirmed detections, the question shifts from whether there is an anomaly to what the anomaly means. Because something happened in the earliest moments of the universe. Something our models did not predict. something our simulations did not produce. Something that left a mark visible now, 13 billion years later, in the light that a golden mirror floating in cold space is gathering, one ancient photon at a time. What that something is remains, for now, unknown. And the deeper you look into the unknown, the larger it becomes. There is a particular kind of vertigo that comes not from height, but from scale. Not from standing at the edge of a cliff and looking down, but from suddenly understanding, truly understanding, in the body as much as the mind, how large the stage really is, how long the play has been running, how small the theater you have been sitting in all along. The James Webb Space Telescope is inducing that vertigo in the scientific community right now. But to feel it fully, you need to understand not just what the telescope is finding, but how extreme the numbers actually are. Because it is one thing to say that galaxies are appearing too early in the universe's history. It is another to stand in front of the actual figures and let them speak. Begin with mass. The Milky Way, the galaxy you live in, the galaxy that contains the Sun and its planets and every living thing ever observed, is estimated to contain somewhere between 100 billion and 400 billion stars. In mass terms, the stellar component of the Milky Way is approximately 50 billion solar masses. That number sounds enormous because it is enormous. Building a galaxy that size, from scratch, from a universe of diffuse hydrogen gas, requires billions of years of continuous star formation, galactic mergers, the recycling of stellar material across multiple generations of stars. It is the product of nearly 13 billion years of cosmic history. Now, consider what the James Webb Space Telescope found in 2023, in a study that sent tremors through the astrophysics community. A collection of galaxies observed at redshifts between 7 and 10, meaning they are being seen as they existed when the universe was between 500 and 800 million years old, that appear to have stellar masses comparable to the Milky Way. Not proto-galactic clumps, not the early fragile seeds of future galaxies. Fully assembled systems, carrying mass that our models say should have required vastly more time to accumulate, already present in the universe before it had even lived through its first billion years. 1 billion years. In a cosmos, now 13.8 billion years old. To feel the weight of this, consider an analogy. Imagine you are an archaeologist. You are excavating a site that historical records indicate was first settled 5,000 years ago. You expect to find simple tools in the earliest layers, hand-shaped clay pots, stone implements, the fragile beginnings of settled life. Instead, in the deepest stratum, beneath everything else, you find a cathedral. A fully constructed, architecturally complex, structurally sophisticated cathedral, complete with stained glass and carved stonework, in a layer that should contain only the first crude attempts at permanent shelter. The cathedral does not belong there. It could not have been built at that time. And yet, there it is, composed of exactly the same stone as everything around it, in exactly the position that the geological record places in the most ancient accessible layer. That is, roughly, the experience of theoretical cosmologists looking at the James Webb data. But the mass anomaly is only one dimension of the problem. There is also the question of morphology, of shape. Galaxies, like living organisms, have life cycles. Young galaxies tend to be irregular, gas-rich, turbulent, blazing with the blue light of massive young stars that burn hot and die fast. As galaxies age, their star formation slows, their gas is depleted, their populations shift toward older, cooler, redder stars. The oldest, most massive elliptical galaxies in the modern universe Enormous spheroids of ancient stars, almost entirely devoid of ongoing star formation, represent the final stage of this cycle. They are the red giants of the galactic world. Their formation and quenching, the process by which star formation shuts down, is thought to take billions of years. The James Webb Space Telescope has found quenched galaxies, galaxies where star formation has already ceased, at redshifts between 4 and 5, meaning it has found galactic corpses in the early universe. Systems that had already lived out their entire star-forming lives and gone quiet before the universe was even 1.5 billion years old. Systems that somehow ran through a process expected to take the age of the solar system in a fraction of that time. Galaxies that were born, flourished, and died before most of the universe had even woken up. This is not a minor discrepancy. This is the cosmos violating its own known schedule. Then there is the matter of supermassive black holes. At the center of nearly every large galaxy lies a supermassive black hole, an object millions or billions of times more massive than the Sun, compressed to a region smaller than the solar system, around which the entire galactic structure organizes itself. The supermassive black hole at the center of the Milky Way, known as Sagittarius A, is approximately 4 million solar masses. The one at the center of M87, famously imaged by the Event Horizon Telescope in 2019, is 6.5 billion solar masses. These objects are extraordinary, and their formation, like galaxy formation, is expected to be slow, the product of billions of years of mergers, accretion, and the collapse of massive stars. James Webb has detected active supermassive black holes, quasars, blazing with the energy of gas falling into them at enormous rates, at redshifts above 7, meaning it has found black holes containing billions of solar masses in a universe less than 800 million years old. The theoretical mechanisms for forming black holes, that large, that fast, are insufficient. The physics of accretion, of feeding matter into a black hole, has rate limits imposed by radiation pressure, a ceiling known as the Eddington limit. To reach a billion solar masses in under a billion years requires either starting from an unusually large seed and accreting near the theoretical maximum the entire time, or violating the known constraints in ways that are not well understood, or both. These black holes, by existing when they do, imply processes in the early universe that are either invisible in current models or simply absent from them. Step back further, and the picture becomes even more disorienting. The James Webb Space Telescope has now confirmed galaxy candidates at redshifts above 12, and claims of detections at redshift 16 and even higher are under investigation. Redshift 16 corresponds to a universe approximately 250 million years old, a quarter of a billion years after the Big Bang. At that epoch, according to the Standard Model, the universe should have been in the late stages of its dark ages, the very first stars perhaps only recently forming, the first proto-galactic structures still assembling from primordial gas, nothing remotely approaching the light-gathering complexity of a galaxy. And yet, there are signals in the data. Faint, contested, requiring confirmation. But there, if any of those detections are confirmed as genuine galaxies at those distances, at redshifts above 15, the implications for the Standard Model are not merely uncomfortable. They are, by the word chosen carefully, catastrophic. Not in the sense of disaster, but, in the original Greek sense, a turning over, an overturning, a structural reversal of what was assumed to be stable ground. The universe has shown us, repeatedly throughout the history of science, that it is not obligated to conform to our frameworks. It does not negotiate, it does not apologize, it simply is. And we either update our understanding to match it, or we continue to mistake our models for reality. What James Webb is forcing us to confront is the possibility that somewhere in the architecture of our best cosmological theory, something is missing, or something is wrong. And in science, the word wrong at this scale does not mean a small correction. It means a rethinking, a restructuring of what we thought we understood about how the universe began, how it built itself, and what conditions made possible the emergence of everything that exists, including you. Including this moment of recognition, this very act of looking up and realizing that the story you were told about where everything came from may be incomplete in ways that reach all the way down to the ground you stand on. That is not a comfortable thought, but it is an honest one. And the discomfort, it turns out, is only going to grow. Science is not a collection of facts. It is a collection of questions that have temporarily found satisfying answers. And the most dangerous moment in any scientific field is not when everything is uncertain. That state is honest, manageable, navigable. The most dangerous moment is when everything seems settled, when the framework feels complete, when the model works so well for so long, across so many different observations, that the scientists working within it begin to confuse the map for the territory. Cosmology arrived at something close to that dangerous moment in the early years of the 21st century. The standard model of cosmology, lambda CDM, had by then achieved something remarkable. It unified the physics of the very early universe with the observed structure of the cosmos today in a single mathematically coherent framework. It incorporated general relativity, the physics of the hot early universe, the behavior of dark matter as a gravitational scaffold for galaxy formation, and the accelerating expansion of space driven by the mysterious energy density called dark energy. It was tested against the cosmic microwave background, against the large-scale distribution of galaxies, against the abundances of light elements, against the distance luminosity relationships of Type Ia supernovae. Every time it was tested, it held. This is not a small thing. The history of science is littered with theories that held across a wide range of observations before ultimately failing at some previously unexplored extreme. Newtonian mechanics worked perfectly until the speeds approached that of light and the gravitational fields became extreme enough to require general relativity. Classical electromagnetism worked perfectly until atomic scales demanded quantum theory. Every major theoretical revolution in physics began with a model that had worked, genuinely worked, until it met conditions it had never been designed to describe. Lambda CDM is now meeting such conditions, the extreme edge of the observable universe. The deep time regime that the James Webb Space Telescope is accessing for the first time is precisely the region where the model's predictions for structure formation are most sensitive to its underlying assumptions. And those assumptions include several that have never been fully testable until now. One of the deepest assumptions concerns the nature of dark matter. Dark matter is one of the most successful invisible entities in science. We cannot see it. We cannot detect it directly with any instrument. We cannot capture it, manipulate it, or confirm a single particle of it in a laboratory. And yet its gravitational effects are visible everywhere in the cosmos, in the way galaxies rotate faster at their outer edges than their luminous matter alone can explain, in the way clusters of galaxies bend light from objects behind them more strongly than their visible mass predicts, in the large-scale structure of the cosmic web, the vast network of filaments and voids that organizes matter across hundreds of millions of light years. Dark matter is the skeleton of the universe. Without it, the mathematics of structure formation collapses. In the lambda CDM model, dark matter is cold, meaning it moves slowly relative to the speed of light, clumps easily under gravity, and forms the dense halos around which normal matter accumulates into galaxies. Cold dark matter works beautifully at large scales, but it makes specific predictions about the sizes, masses, and numbers of the first galaxies to form. And those predictions are now facing scrutiny from the James Webb data in ways that are not yet resolved. If dark matter behaved differently in the early universe, if it was not cold but warm or fuzzy, if its particle properties allow interactions that cold dark matter forbids, the timeline and character of early structure formation could differ substantially from what lambda CDM predicts. Some theoretical physicists have proposed that dark matter particles with a mass in a certain range, called fuzzy dark matter, would exhibit quantum mechanical wave-like behavior on galactic scales, suppressing the formation of very small structures while potentially accelerating the collapse of larger ones. It is speculative, but it is not without motivation, and the James Webb data has given it renewed attention. Then there is the matter of the cosmological constant. In 1917, Albert Einstein added a term to his field equations of general relativity, a constant he called lambda, to counterbalance gravity and produce a static universe, which was the prevailing assumption at the time. When Edwin Hubble's observations in the late 1920s revealed that the universe was in fact expanding, Einstein famously discarded lambda, calling it his greatest blunder. But in 1998, observations of distant supernovae revealed that the expansion of the universe is not just continuing, it is accelerating. Space itself is expanding faster and faster, and to account for this, the cosmological constant was reinstated, now interpreted not as a device to hold the universe static, but as a description of the energy density of the vacuum, the mysterious dark energy that drives the acceleration. The problem is that no one understands what dark energy actually is. Quantum field theory predicts a vacuum energy density that should be between 60 and 120 orders of magnitude larger than the value the cosmological constant has to take in order for the observed expansion rate to be correct. This discrepancy, the largest known disagreement between two successful physical theories, has been sitting at the foundation of cosmology for decades, like an unexploded device that everyone has agreed, tacitly, not to touch too forcefully. What if the cosmological constant is not actually constant? What if dark energy has evolved over the history of the universe? Recent data from the Dark Energy Spectroscopic Instrument, released in 2024, suggested that dark energy may not be perfectly constant, that its value may have changed slightly over cosmic time. If true, this would open a door to revisions in the expansion history of the universe that could, in principle, affect the timeline of structure formation and potentially accommodate some of what Webb is seeing. Or it could introduce new complications that make the picture even harder to resolve. But perhaps the deepest challenge posed by the James Webb anomalies touches something more fundamental than dark matter physics or the equation of state of dark energy. It touches the initial conditions. The Standard Model begins the story of the universe at a very particular moment. Just after the Big Bang, in a state described by specific values of density, temperature, and the statistical pattern of quantum fluctuations that seeded all future structure. The theory of cosmic inflation, the extraordinarily rapid exponential expansion thought to have occurred in the universe's first tiny fraction of a second, is what the Standard Model invokes to explain why those initial conditions take the precise values they do, why the universe is so flat, so homogeneous on large scales, yet so precisely imprinted with the small density variations that eventually grew into galaxies. Inflation is, in the words of many physicists, almost certainly right, in the sense that something like it must have happened to explain what we observe. But the details of inflation remain poorly constrained. Different inflationary models predict different statistical properties of the primordial fluctuations. And if the fluctuations were different, if they were more intense, more concentrated, or distributed differently than the simplest inflationary models predict. The first structures to form from them could have been more massive, more numerous, and more organized than the standard model's predictions would suggest. In other words, the anomalies Webb is seeing may not indicate that structure formation was faster than expected. They may indicate that the initial conditions from which structure formed were different than expected, that the universe was set up from its very first instance in a way that our current models have not fully captured. This is the paradox at the center of everything. The tool built to confirm the cosmological model may instead be revealing the limits of that model. The machine designed to answer the origin question has opened a deeper version of the same question. And the scientists who built it, who calibrated it, who turned it toward the sky with decades of intellectual investment in a beautiful and coherent framework, they are now reading its data with the particular mix of exhilaration and dread that comes from realizing the framework may need to grow larger than the mind that built it. To look at the universe and see something that should not be there is one kind of discovery. To look at the universe and realize that you did not know what you were looking for, that is another kind entirely. And it is the second kind that changes everything. Every crisis in science has a grammar. It begins with an anomaly, a single data point, a stubborn discrepancy, something that does not quite fit. The first instinct is always the same: find the error, check the instruments, recalibrate, repeat the measurement. The anomaly is assumed to be a symptom of imperfection in the observation, not imperfection in the theory, because the theory has earned its presumption of correctness through years of successful predictions. Only when the anomaly survives every attempt at elimination, only when it replicates and deepens and begins to appear in independent datasets collected by different instruments using different methods, only then does the grammar shift. The anomaly becomes a problem. The problem becomes a challenge. The challenge, if it cannot be absorbed, becomes a revolution. Cosmology is somewhere between challenge and revolution right now. And to understand why the James Webb anomalies are so resistant to resolution, you need to understand the specific mechanisms by which the standard model says galaxies should form, and precisely where those mechanisms are straining under the weight of the new observations. Galaxy formation begins with dark matter. Not with gas, not with stars, not with any of the luminous matter we can see. In the standard picture, cold dark matter collapses first, forming invisible gravitational structures called dark matter halos. These halos grow hierarchically, small halos forming first, then merging into progressively larger ones over time, and their gravitational wells are what draw ordinary matter in. Gas falls into the dark matter halos, cools, condenses, fragments, and eventually reaches densities and temperatures at which nuclear fusion ignites. Stars are born. And from the accumulation of those stars, from the feedback of their radiation, and the explosions of their deaths, from the chaotic chemistry of gas mixing and cooling and heating over millions of years, galaxies emerge. This process is not fast because it cannot be fast. Every step is governed by physics that imposes timescales. The collapse of a dark matter halo from a small density fluctuation takes hundreds of millions of years. The cooling of gas to the temperatures required for star formation has its own timescale, governed by the density and composition of the gas. The growth of a stellar population large enough to constitute a massive galaxy requires sustained star formation over extended periods. Not a burst that assembles everything at once, but a long accumulation, interrupted by the very stars being born, whose radiation and explosive deaths push back against the gas trying to collapse around them. This pushing back, called stellar feedback, is one of the central mechanisms regulating galaxy formation. Massive stars emit enormous amounts of ultraviolet radiation that ionizes and heats the surrounding gas, preventing it from collapsing further. When those stars die as supernovae, they drive powerful winds that can blow gas out of a galaxy entirely, quenching further star formation. The balance between gravity pulling gas in and stellar feedback pushing it out determines the rate at which a galaxy can grow. It is a self-regulating cycle, and it places real, physical limits on how fast a galaxy can build its stellar mass. The James Webb anomalies suggest that something in the early universe disrupted this balance, or that the balance worked differently then than it does now. One possibility that theorists have begun seriously exploring is that the first generation of stars, population 3 stars, those primordial giants of pure hydrogen and helium, were dramatically more massive and more numerous than any surviving models have assumed. If those early stars were routinely hundreds or even thousands of times the mass of the Sun, something that the absence of heavy elements in primordial gas may have permitted, then the first stellar generations would have lived fast and died explosively, seeding the universe with metals and ionizing radiation at rates far beyond what standard simulations produce. The enhanced enrichment of the early intergalactic medium could have altered the cooling rates of gas in subsequent generations of forming galaxies, allowing star formation to proceed more efficiently and galaxies to assemble more mass in less time. This is speculative, but it is not arbitrary. The physics of metal-free gas cooling in low metallicity environments genuinely does allow for the formation of stars far more massive than anything found in the contemporary Milky Way, where the presence of carbon, oxygen, and other elements provides efficient cooling channels that fragment gas clouds into smaller, less extreme objects. Remove those metals, as the primordial universe requires, and the gas can only cool through molecular hydrogen, a less efficient process that allows cores to grow much more massive before igniting. The first stars may have been monsters by any modern standard, and their deaths may have left the early universe in a state very different from what our simulations have assumed. Another mechanism under investigation is the role of supermassive black hole seeds. In the Standard Model, the supermassive black holes found at the centers of massive galaxies today grew from much smaller seeds, the remnants of the first massive stars, perhaps a few hundred solar masses, through billions of years of accretion and mergers. But the black holes Webb is finding in the early universe, billions of solar masses present before the universe's first billion years, cannot plausibly have grown from such modest seeds in the available time, even accreting at the theoretical maximum rate without interruption. This has led to renewed interest in a class of objects called direct collapse black holes. In regions of the very early universe, where the normal channels of star formation were suppressed, perhaps by intense ultraviolet radiation from nearby galaxies, preventing molecular hydrogen from cooling and fragmenting the gas. Vast clouds of gas could potentially have collapsed directly into black holes of tens or hundreds of thousands of solar masses, bypassing the stellar stage entirely. These heavy seeds would have a substantial head start in the race to become the supermassive black holes observed at high redshifts. The existence of direct collapse black holes remains unconfirmed, but the James Webb Space Telescope is actively searching for their signatures, specific patterns of emission that would distinguish them from ordinary stellar mass black hole formation. And then there is the issue of star formation efficiency. In the Standard Model, galaxies are thought to convert gas into stars with a relatively low efficiency. Only a few % of the available gas in a dark matter halo ends up locked in stars at any given time, with the rest being kept diffuse by feedback processes. But some of the most massive early galaxies detected by Webb appear to have stellar masses that require star formation efficiencies approaching or exceeding 100%, meaning they seem to have converted nearly all of their available gas into stars in a very short period. This is physically extraordinary. It implies either that the gas supply was dramatically larger than models predict, or that feedback mechanisms were somehow suppressed in these early systems, or that both things happened simultaneously. One intriguing possibility is that the early universe, before it was substantially enriched with metals, and before the reionization of the intergalactic medium was complete, provided conditions that temporarily suspended the usual regulatory mechanisms. Without metals, stellar feedback was less efficient. Massive stars died quickly, but the mechanical coupling of their energy to the surrounding gas was weaker. Without a fully ionized intergalactic medium, gas infall onto proto-galaxies could have been smoother and more sustained. In this view, the first few 100 million years of the universe were a brief window of abnormally efficient galaxy formation, a phase of cosmological construction that ran faster and hotter than anything that has occurred since, before the universe's own stellar generations began to moderate the pace of their own creation. If this is correct, then the James Webb anomalies are not evidence that the Standard Model is wrong in any fundamental sense. They are evidence that the early universe was genuinely different from the late universe, that the same physics operated under conditions that produced qualitatively different outcomes. The rules did not change, but the boundary conditions in which those rules played out were extreme enough to push the system into regimes that the models, calibrated primarily on the modern universe, had not adequately anticipated. But here is the difficulty with that reassuring framing. It requires calibration. It requires knowing, with some precision, what those early conditions actually were. The metallicity of the gas, the intensity of the radiation background, the masses of the first stars, the sizes of the black hole seeds, and those are exactly the quantities that are least constrained by observation, because the epoch in which they matter most is the one that was, until the James Webb Space Telescope, essentially invisible to us. We have, in other words, been building models of the early universe on inference and extrapolation, with very little direct observational constraint. And now, for the first time, those models are meeting direct observations, and the meeting is not entirely comfortable. What Webb is doing, at its deepest level, is not just discovering new objects. It is providing, for the first time, the empirical data needed to test ideas that have been theoretical for decades. It is placing constraints, real, hard, observational constraints, on the physics of the epoch that gave birth to everything. And in doing so, it is forcing the theoretical frameworks to evolve, to stretch, in some cases, to fracture. The mechanisms are real. The physics is real. The questions are legitimate, and the scientists pursuing them are working at the highest level of rigor. But what all of it adds up to, in the view from outside the equations, is something both thrilling and unsettling. A portrait of a universe whose early history was more extreme, more productive, more structurally complex than we imagined. And a portrait painted by an instrument that has barely begun its work. The anomalies are not going away. If anything, with each new cycle of observations, they are getting sharper. There is a pattern to how scientific revolutions unfold, and it is almost never the clean, dramatic rupture that popular history describes. It is not a single genius making a single discovery that overturns everything overnight. It is, instead, a slow accumulation of pressure, anomaly upon anomaly, discrepancy upon discrepancy, building behind a theoretical wall that looks solid from the outside, but has been developing cracks that the people closest to it have known about. Quietly, for years, the wall holds, the wall holds, and then, eventually, it does not hold, and the flood of new understanding that rushes through is mistaken for suddenness when it is actually the culmination of a long, quiet, unresolved tension. Cosmology is behind such a wall right now, And the tension is not limited to the James Webb anomalies. It extends outward in every direction, touching unresolved problems that predate the telescope's launch, that have been politely coexisting with the Standard Model for decades. Taken individually, each of these tensions might be explainable. Taken together, they begin to suggest something more serious: that the Standard Model of cosmology, for all its extraordinary success, may be approaching the boundaries of its own domain of validity. Consider the Hubble tension, the expansion rate of the universe, a quantity astronomers call the Hubble constant, measured in kilometers per second per megaparsec, can be measured in two fundamentally different ways. The first way is to measure it directly, using the observable universe as it exists today, mapping the distances and recession velocities of galaxies, calibrated through a chain of standard candles that begins with Cepheid variable stars and extends to Type Ia supernovae. This is the local measurement, and it currently returns a value of approximately 73 kilometers per second per megaparsec. The second way is to infer the expansion rate from the cosmic microwave background, the ancient relic radiation left over from the early universe, using the standard cosmological model to propagate the early universe's physics forward in time to predict what the expansion rate should be today. This method returns a value of approximately 67 kilometers per second per megaparsec, 67 versus 73. That gap is, in absolute terms, modest. In statistical terms, it is enormous, now exceeding 5 sigma of confidence, meaning there is less than a 1 in a million chance that the discrepancy is due to random measurement error. Both methods have been refined and cross-checked repeatedly by independent teams using independent data. The tension has not gone away. It has grown. It is now considered one of the most significant unresolved problems in modern physics, and its resolution, when it comes, may require changes to the Standard Model that extend well beyond a simple parameter adjustment. The Hubble tension is not the James Webb anomaly. They are separate observations, measured at different epochs, using different methods, probing different aspects of the cosmic model. But they point in a coherent direction. The Standard Model, in its current form, may be inconsistent with itself. The universe it describes at early times may not evolve into the universe we observe at late times as seamlessly as the model assumes. Something in the middle may be missing, or something at the beginning, or, more unsettlingly, something in the framework's underlying assumptions that is so deeply embedded that it is invisible until the data from opposite ends of cosmic history refuses to align. Then there is the S8 tension, a discrepancy between the amount of clumping of matter predicted by the Standard Model and the amount actually observed in surveys of the large-scale structure of the universe. The model predicts that matter should be clumped slightly more than observations suggest. Small discrepancy, some would say, but it adds to the list. Another tension, another place where the model's predictions and the universe's behavior diverge just enough to notice, not enough, yet, to force a conclusion. And beyond the tensions within observational cosmology, there are the theoretical absences. Dark matter has been the subject of direct detection experiments for decades. Particle physics experiments buried deep underground, surrounded by shielding to block every known source of background radiation, have been listening for the signature of a dark matter particle interacting with ordinary atoms and hearing nothing. The leading candidate particles, called WIMPs, weakly interacting massive particles, have had their parameter space narrowed by increasingly sensitive experiments to the point where much of the theoretically favored region is now excluded. Dark matter is gravitationally real and observationally overwhelming, but its particle nature remains entirely unknown. Dark energy is more mysterious still. It constitutes approximately 68% of the total energy content of the universe. It is the dominant component of the cosmos, and we have no physical understanding of it beyond the mathematical description of its effect, a term in an equation. Whether it is a true constant of nature, as the cosmological constant implies, or a dynamic field that evolves over time, as many theoretical alternatives propose, is an open question, and the resolution of that question would have profound implications for the long-term fate of the universe. Whether it expands forever, accelerates toward a cold and diffuse emptiness, or undergoes some dramatic future transition that our current physics does not predict. What the James Webb Space Telescope is doing in this broader context is not introducing an isolated anomaly into an otherwise healthy model. It is adding pressure to a structure that was already under pressure from multiple directions simultaneously. The anomalous galaxies at high redshift are not the only crack in the wall. They are the newest crack, and perhaps the most visible, because they come with images, gorgeous, arresting, undeniable images of things that should not exist, presented to the world with a clarity that numerical data tables and statistical plots cannot quite convey. When you can see the anomaly, when you can point to a photograph and say, "That galaxy should not be there. It is too big, too structured, too old for its time," the weight of the discrepancy becomes real in a way that a sigma value in a paper cannot fully achieve. There is something else the James Webb findings are forcing into sharper focus: the question of what the observable universe actually represents. The observable universe, the sphere of space whose light has had time to reach us since the Big Bang, has a radius of approximately 46 billion light-years. That number accounts for the expansion of space during the time the light was traveling. The observable universe contains an estimated 2 trillion galaxies. It is vast beyond any meaningful intuition, and yet it is, emphatically, not all there is. It is a bubble of visibility inside a cosmos that extends beyond it in every direction, possibly without limit. What lies beyond the observable horizon is not empty. There is no reason to believe the universe simply stops at the edge of what we can see. There may be more universe out there. There is almost certainly more universe out there. But it is, in the most absolute sense possible, invisible to us. Not because of any failure of instrumentation or technology, because the light from those regions has not had time to arrive, and because the universe is expanding faster than light can cross the growing distances, it never will. This means that the James Webb Space Telescope, for all its extraordinary power, is not seeing the universe. It is seeing a portion of the universe, the portion visible from our specific location, at this specific moment in cosmic time. The boundary of the observable universe is not a wall in space. It is a wall in time. And behind that wall, the cosmos continues, on scales we cannot see, possibly containing structures we cannot imagine, obeying, perhaps, physics we have not yet formulated. When scientists observe massive, unexpected galaxies at the edge of the observable universe, they are looking at a region of space that is, in a very real sense, at the intersection of the knowable and the unknowable. The galaxies are just barely within reach. Their light has just barely arrived after its billions of years' journey. A little farther, and they would be forever invisible. They are, in some sense, the last witnesses in a court whose jurisdiction ends at the horizon, and the testimony they are giving does not match the theory of the case. What this means for cosmology, for the actual practice of science, for the revision and extension of models and the design of future observations, is the subject of enormous ongoing effort. Multiple explanations are being pursued in parallel, with the rigor and skepticism that the field demands. But what it means at a deeper level, at the level of how we understand our own position in relation to the cosmos and the limits of our knowledge, is something that science can point toward but that each person must ultimately confront alone. Because at some point, the questions stop being about galaxies, and they start being about us. There is a question that scientists rarely ask out loud, not because it is unscientific, but because it is too large to fit inside a research paper. It is the question that lives underneath the equations, behind the redshift measurements, in the silence between data points. It is the question that the James Webb Space Telescope, by doing its job with extraordinary precision, has forced back into the open with a kind of quiet violence. If the universe built itself differently than we thought, if the first galaxies formed faster, if the first black holes grew larger, if the first stars were more extreme than any model predicted, then what does that mean for the chain of events that eventually produced us? This is not a sentimental question. It is a structural one. The emergence of life, as far as we understand it, depends on a precise sequence of cosmic events. Stars had to form and die to produce the heavy elements, carbon, nitrogen, oxygen, phosphorus, sulfur, that complex chemistry requires. Those elements had to be dispersed through the interstellar medium by stellar winds and supernova explosions. Second and third generation stars had to form from that enriched material, dragging along planetary systems in their wake. Those planets had to exist in the narrow thermal zones where liquid water is stable. And then, on at least one such planet, the chemistry of those heavy elements had to organize itself into self-replicating molecules. Those molecules into cells, those cells into organisms, those organisms into minds capable of eventually turning their attention upward and asking how they got here. Each of those steps is sensitive to the conditions that preceded it. The abundance of heavy elements in the present universe depends on how many stellar generations have lived and died before now. The age of the solar system, 4.5 billion years, sits at a particular point in cosmic history that is neither too early, when the universe was too metal-poor to form rocky planets easily, nor so late that the Sun would be peculiar among its neighbors. The very timing of our existence is embedded in the timeline of cosmic evolution. Now consider what happens to that picture if the early universe was more productive than the standard model suggests. If galaxies formed faster and more efficiently in the first billion years, then the first generation of heavy elements was seeded into the intergalactic medium earlier than the models predict. If those elements were available sooner, then the conditions for rocky planet formation arrived sooner. And if rocky planets in habitable zones were forming 1 billion years earlier than our models assumed, potentially forming around stars that lived and died long before our Sun was born, then the question of when life could first have arisen in the universe shifts backward in a way that is not trivial. The universe, if the James Webb observations are borne out, may have been biologically viable, may have contained the necessary chemical ingredients for the emergence of life, earlier in its history than we thought. Not by a small margin, by potentially hundreds of millions of years. And in a cosmos 13.8 billion years old, that margin is not merely chronological. It is the difference between one epoch of possible life and several. It is the difference between rare and potentially common. It is the difference between a universe in which we are early arrivals and one in which we might, cosmically speaking, be late. This possibility that intelligence-bearing civilizations could have arisen in the universe far earlier than any timeline anchored to our own origin would suggest, sits at the heart of what is sometimes called the Fermi paradox in a new and more acute form. The original paradox, posed informally by physicist Enrico Fermi in 1950, asked a deceptively simple question. If intelligent life is possible, and the universe is old enough for it to have arisen many times over, then where is everybody? Where are the signals, the artifacts, the evidence of civilizations that preceded us by millions or billions of years? The James Webb anomalies deepen the paradox without resolving it. If the early universe was more fertile than we thought, if massive, metal-enriched galaxies existed when the cosmos was only a few 100 million years old, then the window for life's emergence is wider, earlier, and potentially richer than our models have assumed. The silence of the cosmos, if it is indeed silence, becomes more difficult to explain, or the silence itself becomes data. Evidence not of absence, but of something we do not yet understand about the relationship between chemistry, time, and the emergence of complexity. But the implications of the James Webb findings do not stop at biology. They reach further into territory that is more speculative but no less real for being so. If the standard cosmological model is incomplete, if there is physics operating in the early universe that our current framework does not capture, then there may be phenomena, forces, or structures in the cosmos that are not merely unknown to us, but that we have no theoretical vocabulary to describe. The history of physics is in part a history of discovering categories of reality that were invisible until the instruments to detect them existed. Magnetic fields were invisible until certain materials revealed them. Electromagnetic waves were invisible until the mathematics of Maxwell predicted them and the experiments of Hertz confirmed them. Gravitational waves were predicted by Einstein in 1916 and remained undetected for a century until the extraordinary sensitivity of interferometers made their observation possible. Each of these discoveries did not merely add a new item to the catalog of known things. Each one restructured the catalog itself. What the James Webb Space Telescope may be doing, in its patient accumulation of ancient photons at the edge of the observable universe, is revealing the silhouette of a restructuring that has not yet happened. The anomalous galaxies are not themselves the new physics. They are shadows cast by it. They are the observational signature of processes that our models do not contain and cannot currently explain. The new physics, whatever it turns out to be, is what produced those galaxies. The galaxies are the evidence. The explanation is still being written. And the writing of that explanation will require not just more data, though more data is essential. It will require what the most transformative moments in the history of science have always required: a willingness to question assumptions so deeply embedded that they have become invisible. To look at the foundations of a framework that has worked beautifully and ask not just what it predicts, but what it assumes. Not just what it describes, but what it excludes. Not just where it succeeds, but where the edges of its success are and what lies beyond those edges. This is uncomfortable work. It is uncomfortable because the assumptions that are hardest to see are the ones that have been most thoroughly absorbed into the way a field thinks. The assumption that the cosmological constant is truly constant. The assumption that dark matter is cold and collisionless. The assumption that the inflationary initial conditions are well described by the simplest models. The assumption that the large-scale structure of the universe is statistically isotropic, the same in every direction. These are not arbitrary guesses. They are the best available descriptions of what the universe appears to be. But appearances in the history of science have a way of changing with the quality of the instruments doing the looking. The James Webb Space Telescope is the sharpest instrument humanity has ever aimed at deep time. And deep time, it turns out, is not what we expected. There is one more consequence of all this that is rarely discussed in the scientific literature, because it is not a consequence in the technical sense. It is a consequence for us, for the beings doing the observing, the questioning, the theorizing, for the civilization that built a golden mirror and sent it to float in the cold between the earth and the sun, pointed at the ancient light. Every time science reveals that the universe is larger, older, more complex, and more extreme than the previous generation's best model predicted, it is not merely expanding the domain of knowledge, It is recalibrating the sense of scale at which human existence registers. The universe of Newton was local, mechanical, comprehensible. The universe of Einstein curved and dilated, resistant to intuition but still bounded in imagination. The quantum universe added layers of irreducible uncertainty, probabilistic foundations beneath the apparently solid floor of classical physics. And now, the cosmological universe, as revealed by James Webb, is gesturing toward something stranger still. An early history more turbulent and more structured than we knew, populated by objects whose existence strains the best theories we have, whose light carries information about conditions we have never directly studied, and processes we have not yet named. To look at a photograph of a galaxy that should not exist, in a universe that should not have been able to produce it yet, is to feel something that is hard to name precisely, but that has something of awe in it, and something of vertigo, and something that might be described as the specific loneliness of knowing. The loneliness of a species that is conscious enough to ask where it came from, and smart enough to realize that the answer is not yet fully in reach. That feeling is not a flaw. It is a compass. It is the sensation that has driven every genuine advance in the history of human understanding. And it is pointing, right now, directly at the edge of the observable universe, where the light is old and the galaxies are wrong, and the next chapter of what we know about everything is quietly, inexorably, being written. There is a word that appears frequently in the scientific literature on the James Webb Space Telescope findings. It appears in titles of papers, in the conclusions of studies, in the careful language of astronomers who have spent their careers building the framework that the telescope's observations are now straining. The word is unexpected. Unexpected mass, unexpected structure, unexpected quenching, unexpected black hole growth, unexpected, unexpected, unexpected. A word that in ordinary usage means merely surprising, but that in the vocabulary of science carries a specific and serious weight. To say that an observation is unexpected is to say that a prediction was made, that the prediction was based on a tested and trusted model, and that the observation does not match. It is to say that the universe, once again, has declined to behave as instructed. This has happened before. It will happen again. And each time it happens, the same drama unfolds. The initial denial, the search for instrumental error, the slow acceptance, the theoretical scramble, and finally, sometimes after decades, sometimes after generations, the restructuring of understanding that absorbs the anomaly and emerges larger and stranger and more honest than what preceded it. But this time, something is different about the scale of the reckoning. Not because the anomalies are necessarily larger than those that preceded previous revolutions, though they may be. Not because the model being challenged is more entrenched than Newtonian mechanics was before Einstein, or classical physics before Planck and Bohr, though lambda CDM is extraordinarily well tested and will not be abandoned without extraordinary cause. What is different this time is the vantage point. The James Webb Space Telescope is not observing a local discrepancy, a specific phenomenon, a particular class of object at a particular scale. It is observing the universe at the very limit of the observable, at the cosmological horizon, at the boundary of light travel time, at the edge of the bubble of visibility within which all of human history, all of human science, all of human everything is contained. To find anomalies at that boundary is to find them in the place where the foundations of the structure are laid. Not in the upper floors, not in the decorative details, but in the bedrock, in the initial conditions, in the first moments, in the epoch that everything else depends on. If the foundations are different from what we assumed, then the structure built on them, our entire cosmological narrative, must be re-examined from the ground up. Not necessarily replaced, but re-examined, rebuilt where necessary, made more honest. And that is not a crisis. That is science working. This is, perhaps, the deepest and least comfortable insight that the James Webb Space Telescope is offering. Not about the universe, but about the nature of the knowledge we have accumulated about it. Every cosmological model ever constructed has been, at its core, an act of inference. We cannot step outside the universe to observe it from above. We cannot replay the Big Bang. We cannot run controlled experiments on the formation of galaxies. We can only gather the light that reaches us. Light that has been traveling for billions of years. Light that carries information about conditions that no longer exist. Light that is already ancient by the time it arrives. And from that light, reason our way backward toward what must have been. This is a profound epistemic constraint, and it means that every model of cosmic origins is, necessarily, an extrapolation from limited data into a domain that is, by definition, beyond direct human experience. We are always, when doing cosmology, doing something like archaeology, reconstructing a past we cannot visit, from traces left in a present we can barely decipher, using tools whose limitations we are still discovering. The James Webb Space Telescope is a new and better tool, and new and better tools, in the history of archaeology, have a consistent record. They show that the past was more complicated than we thought, that the civilizations were older, or larger, or more interconnected, that the timelines were wrong, that what looked like a beginning was actually a middle, and what looked like simplicity was actually depth not yet measured. The deep past of the universe is no different. Stand, for a moment, with this image in mind. Somewhere in the data archive of the James Webb Space Telescope, in a file containing infrared photons gathered over hours of observation of a small, dark patch of sky, there is the light of a galaxy that existed when the universe was 400 million years old. That galaxy contained billions of stars. Those stars burned and exploded and seeded space with elements. Some of those elements eventually found their way into other galaxies, other stars, other planetary systems. And somewhere in the 13 billion years between that galaxy's existence and this present moment, in some sequence of stellar births and deaths and planetary formations that stretches across the entirety of cosmic time, the atoms that were once part of that early galaxy made their way into you. Not metaphorically, not poetically, physically. The carbon in your cells, the oxygen in your lungs, the iron in your blood. These are elements forged in the interiors of stars and distributed across the cosmos by their deaths. Some of those stars burned in the early universe. Some of the light the James Webb Space Telescope is collecting may have originated in the very galaxies whose stellar generations eventually produce the atoms that constitute your body. You are, in the most literal sense available to chemistry and astrophysics, a product of the early universe, a downstream consequence of those first, anomalous, unexpectedly massive, structurally precocious galaxies that should not have existed but did. And now you are looking back at them. This is not a rhetorical flourish. This is a physical reality. The universe has, through 13 billion years of stellar nucleosynthesis, gravitational collapse, planetary chemistry, biological evolution, and the slow accumulation of cognitive complexity, arranged itself in such a way that a portion of it can turn its attention toward its own beginning. The James Webb Space Telescope is not separate from the universe it observes. It is made of the same atoms. It was built by beings made of the same atoms. The light it catches is the light of the same universe of which it is a part. The observation is the universe observing itself. There is no way to hold that thought without feeling something shift in the architecture of how you see your own existence. And yet, and this is crucial, the looking does not resolve the mystery. It deepens it. Every confirmed galaxy at high redshift that violates the Standard Model's predictions is not an answer. It is a better question. It is the universe insisting, as it always has, that the story is not over, that the framework, however elegant, is not the territory, that the map, however detailed, omits continents. What lies beyond the observable universe, beyond the light travel horizon, in the regions of space from which no photon will ever reach us, is not nothing. It is more universe, more structure, more time, more history, more strange and impossible objects that violate frameworks we have not yet built. The boundary we call the edge of the observable universe is not a wall. It is the horizon of our sight, the line beyond which the universe continues without us, indifferent to whether we can see it, indifferent to whether it fits our theories, indifferent to whether it makes us comfortable or not. The James Webb Space Telescope has pushed that horizon back a little. It has extended the reach of human sight by hundreds of millions of years of cosmic time. And in the territory it has opened up, it has found not silence, not simplicity, not confirmation, but complexity. Abundance. The deep and slightly disorienting abundance of a universe that was already doing extraordinary things before most of its history had even begun. We are small. We have always been small, but smallness, it turns out, does not preclude depth. The universe spent billions of years building the conditions that would eventually produce a species capable of noticing its own smallness, of measuring the light from the beginning of time, of being troubled by what that light contains. That is not nothing. That is, in fact, the universe's most astonishing achievement. Not its scale, not its age, not the majesty of its galaxy clusters and dark matter webs and colliding black holes. Its most astonishing achievement is that it produced, somewhere in a spiral arm of an unremarkable galaxy, in a region of space that is cosmologically ordinary, beings who could look up, who could be troubled by what they see, who could let the questions stay open. The James Webb Space Telescope is looking at galaxies that should not exist, in a universe that apparently did not follow its own rules. And we are here, assembled from the wreckage of ancient stars, aboard a small planet, with golden mirrors and infrared detectors and the audacity of curiosity, trying to understand why. That effort will not end with a final answer. It will end, as every frontier in the history of knowledge has ended, with a larger question standing where the smaller one used to be. And somewhere beyond the new question, if the pattern holds, another horizon will be waiting. Deeper, stranger, more beautiful, and more honest than the one we are standing at now. Look up. The universe is larger than your model of it. It always has been.